So, a very good afternoon to all. We are at the last part of the lecture, and we are going to start the last lecture of the whole webinar. The lecture will be delivered by Professor Pasquale Serpico of the French National Center for Scientific Research. He is working as a research director there at the Theoretical Physics Lab of NSC. And before getting a permanent position there, he was a PhD student in next rank in Munich. And then he moved to Fermilab as a postdoctoral fellow, and then returned to Europe as a research fellow in France. And then now finally he is at CNRS. And his research interests includes particle cosmology and high energy extraordinary physics, in particular aspects related to dark matter indirect searches. So in this particular talk entitled Indirect Dark Matter Searches, Status and Challenges, we are going to review what we know about the existence and nature of dark matter, putting the strategies used for their identification in a broader context. We will also present the results of ongoing indirect dark matter searches, comparing them in terms of tests of the Wilms paradigm, and then he will discuss the common challenges that this approach has to tackle with, and in particular why the debate often revolves about interpretation of excesses. And finally, he is planning to present a couple of research directions for the road ahead in the next decade. So I welcome Professor Serpico on behalf of the Department of Physics, Assam University, and I will request him to take over, and before that I will start the presentation.
Thank you. Thank you for the introduction.
Yeah. Yeah, just a minute.
Okay.
Here goes your phone. Is it visible?
Yes, I think so. Okay. So thanks to your introduction, I think I can go fast on the first two slides. Basically, I will start. You can pass to the next slide, yes. And so I will start in this menu of the evening on what we know on dark matter, and to recast the search for its identification within the broader context of the cosmological evidence. So please, next slide. What do we know about dark matter? The next slide is a one-slide summary of the dark matter, phenomenon. Basically, there is a number of observations of astrophysical nature and cosmological nature, which only makes sense if you add at least one ingredient beyond the current model of particle physics, plus general relativity. And this ingredient appears to interact only gravitationally. Among these evidences, let me remind you the cosmic microwave background anisotropies, the large-scale structure power spectrum, so the density contrast as a function of the scale, cluster studies, rotation curves of the galaxies, and then body simulations and comparison with observation. That's what these plots, these figures show you. So let's move to the next slide. So for those of you who are not familiar with the scales I'm going to talk about, in terms of the astronomical units, which is the average distance between the Earth and the Sun, the parsec is about 5 orders of magnitude larger. Okay, so the nearest stars are typically at the parsec distances. So this is 5 orders of magnitude larger than the distance from the Earth to the Sun. And if you want to have an idea of the scale of the galaxy, say the radius of the galaxy, that's yet 4 more orders of magnitude, roughly 10 kiloparsec. So the nearest galaxy of a certain size, like Andromeda, is about 1 megaparsec away. And then you need to go 2 more orders of magnitude 100 megaparsec to see the largest features in the distribution of galaxies in the universe. And the features in the statistical properties of the CMB are extend up to, say, 30 gigaparsec. So again, a couple of orders of magnitude more, and this is roughly the size of the observable universe. Okay, so you see that there is a lot of orders of magnitude spanning the phenomenology of cosmological observations. So next slide. So just if you can move to the next slide, I will set this into a context. What I'm showing here is basically what the power of the dark matter phenomenon is. We have a simple effective description of cosmological and astrophysical data on many different scales and at different epochs. So what this plot shows is the mass variance in terms of the average mass. So on the x-axis, you have the mass scale of the observable in question, and on the y-axis, you have the typical fluctuation in mass, the typical contrast in mass characteristic of some different environments, say the fluctuations in the CMB, the large-scale structures, the clusters, and the galaxy at the left part of the plot. Dark matter, as far as cosmology is concerned, is a very simple ingredient, namely it's a stress energy term, the right-hand side of the Einstein equation, which is only described by the density of energy. So if you are not familiar with the Einstein equation, for the students who are not familiar with the Einstein equation that I show here at the bottom left, basically the left-hand side just describes the geometry of the universe, the curvature of the universe, and the right-hand side describes the content, the energy and matter content of the universe. And basically, if we just account for what we know about electrons, protons, neutrinos, and so on and so forth, that's insufficient to explain the data. However, if we just add a single ingredient, some cold species, some energy density which has negligible pressure, then you end up with prediction that in this plot, for instance, are shown by the dashed line, and you see that they match perfectly well the range of scales and structures in the universe, okay, from megaparsec to several gigaparsec scale. Not only that, but this type of effective theory is also predictive. So it behaves like any well-behaved theory that you have learned about in school. In particular, as predicted observations such as the features of the third peak in the CMB angular power spectrum, and also the existence and size and properties of the baryonic acoustic oscillation, which is a feature in the distribution of galaxy at very large scales. So if we now move to the next slide, you should not be so surprised in fact that something like a species interacting only gravitationally can be studied and discovered in astrophysics. I would argue that this phenomenon has happened again and again. In particular, there are historical records such as the discovery of Neptune in 19th century. Basically, this was discovered through gravitational effects that this planet had on the trajectory of Uranus. And but more recently, you have microlensing observations, which are basically exploiting the time dependence of an amplification of the luminous signal from an object due to the gravity of an intervening star to discover brown dwarf or even exoplanets. So in the plot that you see here, it's a simulated light curve due to the gravitational focusing effect of a star, and on the top of it you see the effect of a planetary perturbation. Or more recently, in 2015, we have discovered the existence of very massive black holes, coalescing black holes, just through gravity, once again, through the gravitational wave signal. And this was even awarded a Nobel Prize. And actually, even to this year's Nobel Prize was awarded for discoveries at the Galactic Center of a compact object, which has been discovered through its gravitational influence. So you should not be so surprised about the fact that in astrophysics, people discover, at least initially, some stuff through gravitational phenomena. However, if we move to the next slide, there is something specific of the dark matter, which is what I mean, makes it very interesting for most of us. Maybe if we move to the next slide. Yes, and that's the crucial role of cosmological evidence. And why this is important? For the simple reason that a collection of evidence from the cosmological side not only puts this evidence on a very solid footing, very solid ground, because this is based on linear perturbation theory or exact solutions involving very simple, well-known physics under control, namely gravity, atomic physics for the case of the CMB formation, or basic nuclear physics for the case of Big Bang nucleosynthesis. And so this is a very credible and robust from the physics point of view, but also tells us that most of this stuff behaves as gravitating matter. So there is no evidence whatsoever that the general relativity is breaking down at any scale that we have investigated in cosmology. And also, in this context, in cosmology, we can conclude that whatever is responsible for dark matter, well, that's not accounted for by obvious baryonic species, where baryonic in this cosmological jargon means everything we know about, okay? So basically protons, nuclei, and electrons, and so on and so forth. So we are reasonably sure that this is not due to some very dim compact objects like brown dwarfs or planets that we cannot see. Also, cosmology tells us something about the properties of these species. In particular, it tells about the mass density, of course. That's the defining properties in the fit, if you wish, of the model to the data that I showed before. But also tells us that this must be very, very long-lived. So this phenomenon has been present at least since, I don't know, few tens of thousand years after the Big Bang until now. And the lifetime of this object must be at least an order of magnitude longer than the lifetime of the universe, okay? Also, this matter must be cold, must be non-relativistic. The kinetic energy must be negligible with respect to the rest mass energy. And there are other properties, the fact that the dark matter is not very collisional, so its self-interaction is negligible if compared, say, to the self-interaction of hydrogen atom gas. And it's not dissipative, so there is nothing as efficient as cooling through radiative processes as in known gas in astrophysical systems. Also, it must have very weak interaction with ordinary matter and radiation. So its interaction with not only with protons, electrons, but also with photons and neutrinos must be very weak. And then we have some idea of the mass that this unknown component must have. However, this range is very, very, very broad, from 10 to the minus 21 electron volt per c square up to 10 solar masses or so. So this is a remarkable example of precision cosmology, if you wish, in the context of dark matter. So next slide, please. So there is lots of aspects in this problem, and some of them are extremely good, some of them are extremely bad, and some are even ugly, and people don't like to talk about them. But since the good, the bad, and the ugly is at least a few decades old, I think I can uncover this secret for you. So if we move to this next slide. The good aspect of the dark matter problem is that it requires new physics beyond the standard model. So there is only a handful of indications out there, and this is perhaps one of the most robust ones, and this has stimulated the interest of particle physicists, okay? So this is not unjustified, it's a very good aspect of the dark matter problem. However, there is some bad aspects of it, namely that we have discovered dark matter through gravity, and gravity is universal. So it doesn't tell us anything about the underlying theory, ultraviolet theory, or if you wish, microscopic description that lies below this macroscopic picture. Since gravity is universal, the only way to get an idea of what's going on is to rediscover dark matter through some other channel. Okay, but however, whatever you look for, well, it's going to be model dependent, because now you have to make some assumption on the additional interaction that this species has, and based on this assumption, you may have devise some strategy to look for it, okay? And then if we go to the next item, let me tell you about the ugly aspects of it. So the ugly aspects is that there are models that fulfill all the constraints I talked about, but they are undetectable through other channels, okay? So at least as a proof of principle, we know that there are models where the dark matter identification quest admits untestable solution, okay? So although the dark matter model from the cosmological point of view is quite predictive, it has been tested and till now has passed all tests, in terms of identifying the species responsible for this, well, we are not sure that the problem admits a solution. So all the rest of the talk is going to be relying on this bet and this hope that in fact the dark matter physics is sufficiently rich that we can tackle the problem from a different perspective. Okay. In particular, I will focus on indirect detection strategy, namely trying to sense remotely some effects such as byproducts of annihilation or a decay of dark matter, which can yield information about the dark matter nature. Next slide, please. So let me try to illustrate the contours of this bet with the simplest and most notorious example, but by no way this is unique. Just let me emphasize this for students in particular. Next slide. The traditional link between particle physics and dark matter, which I would trace, say, perhaps to the early 80s, end of the 70s or so, is that in particle physics, at least in theory, there has been a lot of bias, theoretical belief in the fact that there is new physics at the TeV scale. And most of these arguments rely on the so-called hierarchy problem, which can be put in simple terms as the question of why the Higgs, which is a scalar fundamental particle and whose mass should be sensitive to the highest scales present in the theory, in principle even to gravity, well, why is it that its mass is relatively low? So it's even lighter actually than the top quark, okay? In general, this is unexpected, and one of the most popular conjecture is that there is some sort of symmetry that shields some low energy phenomenology from whatever heavy physics is out there, okay? Not only that, but we haven't seen any evidence for new physics at colliders. And one of the reasons to reconcile these negative observation would be to prevent somehow three-level couplings between the standard model particles, which are the blue line in the left diagram schematically represented here, with the new physics represented in red. So if for some reason, for instance, there is some symmetry, sort of parity-like symmetry, which prevents the new physics to be produced as single particles, but allows it to be produced in pairs, say. This has some benefit. For instance, I won't enter details, but for instance, this has benefits with respect to the lifetime of the proton. It makes the proton stable or metastable over a longer time scale in grand unified theories. But what is important for us is that in these new physics scenarios at the TeV scale, imposing such a parity or similar symmetry automatically makes the lightest new particle a stable particle. Okay, so the traditional link of standard model, of beyond standard model particle physics theories with the dark matter scenarios stems from these properties. Maybe there is new particle at the TeV scale, and maybe there is this new particle which is stable because of this sort of protective symmetry. So next slide, please. Till now, till now, everything I said concerns particle physics. What's the impact of adding this new heavy particle in cosmology? Well, the picture of cosmology that you heard about yesterday is that the early universe was very hot, and actually was a plasma where everything that could be thermally produced was produced. In particular, for instance, you had photon-photon collision producing, say, electron-positron pairs. But if you have now a very, and this picture, by the way, has been confirmed indirectly through, for instance, Big Bang nucleosynthesis observations. But if you now extrapolate these scenario to early epochs, say to GeV to TeV scales, well, the particles were energetic enough that they could produce even heavier species. In particular, they could be able to produce these additional stable species that we talked about. And if this is the case, some of these species might still be around, okay? So if you have a new massive particles, which is in chemical equilibrium with the standard model, with couplings of the order of the electroweak strength, what would happen is that it is illustrated in the diagram that you see to the right. This diagram can be described as follows. When the particle was relativistic, so when the temperature was very, very high, basically the number of particles per volume of this volume, which is now expanding with the expansion of the universe, this is known as comoving volume, well, this number of particles was constant. And then you see this as the horizontal flattening line to the left of the plot. However, these particles were kept in equilibrium by some weak scale interactions. And then when the temperature drops below the mass of the particle, most of the particles in the plasma are not capable anymore to produce the extra particle just by kinematical reasons because of the Boltzmann suppression. So only particles in the energetic tail of the plasma would be able to produce it. And at some point, what happens is that the rate of this particle production would be too low compared to the expansion rate of the universe. So this particle would remain, as people say, would freeze out. And so its abundance per comoving volume would become constant. Of course, it would stay in equilibrium longer if the cross-section is larger. So the abundance of this particle is inversely proportional to the annihilation cross-section. So you see that very simple hypothesis. There is a massive stable particle which interacts with, say, electroweak strength, is enough to produce some relic abundance of these species. And next slide. And then you can do a very simple textbook calculation and compute what's the abundance of these species. And it turns out that you can match the cosmological observations if the abundance is, if the mass is of the order of, say, the top quark, and the coupling is of the order of the electromagnetic coupling. Okay, so this is a quite striking coincidence, right? Because one piece of the ingredient comes from cosmology, another piece of the ingredient comes from electroweak physics, and nonetheless, they seem to match pretty well, say within an order of magnitude or so. And this is sometimes dubbed as WIMP miracle, where WIMP stands for weakly interacting massive particle. So next slide, please. This qualitative idea actually is at the origin of a very broad search program for this type of particles. This schematic diagram tries to illustrate this program. The process that I just described, namely the pair production of the standard model particles into dark matter particles and the conversion of dark matter particles into standard model particles, is basically equivalent to read this diagram from left to right or right to left. And of course, if these processes are possible, you can even hope to reproduce it in a collider. And so by colliding protons or electrons, you can hope to produce pairs of dark matter, maybe accompanied by some other signal. Otherwise, this would be clearly invisible at colliders. Or you might also look for annihilating residual annihilations of these particles into dense environments, and so look for byproducts such as photons, neutrinos, positrons, or antiprotons in the byproducts of the annihilation. This is known as indirect detection probe. But you can also read this diagram from the top to the bottom, or from the bottom to the top, so transversally, and this would describe a recoil of this particle against standard model particles. In particular, this might be nuclei. And this is at the origin of the direct detection strategy you have also heard about in some of the previous talk. So the program would be to try to demonstrate that the astrophysical dark matter is the same species that you might produce, say, in a collider or detect in a direct detection experiment underground. And ideally, you would like to reconstruct some of its properties, both from collider or controlled experiments and from astrophysical observations. If they match, well, you have a convincing argument that you haven't discovered what the bulk of the dark matter is, okay? That's the program. If we now move to the next slide, which is more specific of the indirect dark matter searches, this is the left to right arrow in this diagram. You have noticed that among the final states of the annihilation of dark matter particles, you find different standard model particles. In principle, all the standard model stable particles can be found there. Okay, so we are talking about photons, neutrinos, antineutrinos, of course, electrons, positrons, proton, antiprotons, in principle, even light antinuclei or nuclei like deuteron, okay? And you can combine this information in what has been dubbed the multi-messenger approach, trying to correlate the possible evidence in a channel with the expectations that you have in additional channels, okay? So the program here would be to detect stable standard model particles produced remotely, say at the center of a galaxy in a very rich, dark matter-rich environment. And of course, you must take into account that what you inject through the annihilation process might be different from what you observe at the Earth because of energy loss processes, because of diffusive processes, but also that both particle physics and astrophysics determine the abundance of these particles. For instance, in very dense environment, you expect the annihilation rate to be higher, and so to have more secondary particles to detect. Let's move to the next slide. Obviously, because of the very nature of the process we are trying to study, you may basically use different type of instruments to detect the different types of byproducts. Okay, so here is a set of images from different experiments. Some of these you have already seen. For instance, in the left, I'm showing you the ice cube detector with a reconstructed event, a neutrino event in the bottom left. You have also the Fermi Gamma Ray Telescope at the top center, which has provided us wonderful maps in the GeV range, as shown in the top right. And then you have also cosmic ray experiment at the center. You have a balloon, I think it's green. And the bottom picture, you see the AMS cosmic ray detector on board the International Space Station. But you also have indirect cosmological probes as the CMB anisotropy pattern, or even radio signal from the early cosmological epochs, as in the bottom right, you have the edges detector you might have heard about. Okay, each one of these has its own advantages and problems. I won't go through all of this, but if we move to the next slide, you will see that in a typical plot, which is the reach in terms of the sensitivity to the cross-section, annihilation cross-section versus the dark matter mass, several experiments from the cosmological ones to the cosmic ray ones to the gamma ray ones, as shown here by different line colors and styles, they have comparable sensitivity. And actually, we are currently probing the tens to hundreds of GeV mass range for the simplest type of particles that fulfill the WIMP mechanism I was just illustrating before. So till now, we have no clear detection. We have only set bounds, but this is an important plot because it tells you not only that there is some complementary information coming from different sources, but some of these are comparable in sensitivity, but also that basically we are testing the interesting part of the parameter space. If you now move to the next slide, what I want to say is that there have been several claims till now of possible detections through indirect tools. However, one important validation point of any claim of detection is that it should be confirmed by an independent signal in an associated channel. For instance, a gamma ray excess should be associated to a most likely to a positron excess or to a neutrino excess, etc., etc., etc. And not only that, but all claims of excesses interpreted in terms of dark matter till now have been shown to admit alternative explanations, either in terms of astrophysics or in terms, say, of instrumental effects and the like. So if we move to the next slide, I'll try to be schematic here and just list a few of the excesses that you might have heard about. So the galactic center excess is a GeV gamma ray excess in the Fermi-Lat data. The positron fraction excess that goes back at least to the end of the previous decade with Pamela and then confirmed by MS. The antiproton excesses, actually now there are two at least arguments in the antiproton spectrum that are argued to support a dark matter interpretation at hundreds of GeV or maybe a bump at 10 GeV. But let me be generic here and try to illustrate you, and in particular to the students, what are the problems that one has to face in these quests, and why is it that in the last decade there have been many sort of hints or claims or investigations about possible excesses. The reason is that both the signal and the background are actually not very well known. The fact that the signal is not well known actually is often hidden to your eyes because the signal is very well known within a specific model, of course. Whenever you have a theoretical model where you can do computations, you know the signal associated to that model, but nobody actually thinks that any single model presented out there is the truth. Say, even if dark matter is some sort of neutralino in a supersymmetric scenario, that's possible. It's very unlikely that any specific supersymmetric scenario detailed out there represents the true realization in nature, right? So there is some uncertainty related to the ignorance of the underlying true theoretical model. But even the more serious limitation is that the background, which is, by the way, an astrophysical signal most of the time and of interest of its own, is only approximately known. Okay, and this is unfortunately irreducible to some extent because we cannot reproduce astrophysical environments in the lab. So we have to live with it and try to devise a smart strategy. So let's move to the next slide to try to illustrate this problem in a concrete term. Let's say that we are hunting for dark matter, and let's assume that, sorry, the previous one, the previous slide. We are hunting for dark matter, and let's say that dark matter looks like a zebra, okay? Has some peculiar feature, let's say some white and black stripes, okay? And then let's say that, let's move to the next slide. We have an idea of the background, and the background looks somehow similar to the zebra in the sense, sorry, the previous slide, similar to the zebra in the sense that it's a four-legged animal and, you know, living out of grass and leaves. But okay, at first sight, you say, okay, the color is different, the size is different, some of the habits are different, so it should not be so difficult to separate the background from the signal. However, remember that we have just a guess what the background looks like. Okay, so if we move to the next slide, what happens when a new experiment like Fermi, say, starts taking data? What the experiment is really doing is opening a new window in astrophysical space. So maybe it starts collecting some data and you have access to preliminary results of this experiment. And look, these preliminary data are remarkably similar to the type of signal that we are looking at, we are looking for, sorry. So the obvious reaction is that many people start writing dozens of papers about the discovery of dark matter because clearly this matches our expectation for the signal. But then what happens is that the experiment collects more data, and next slide, it reveals a more complete picture of what the situation is, and the more complete picture actually is not so far away from our expectation for the background, in the sense that we have discovered a beast that is belonging to the family of giraffe, but it's remarkably similar in some aspects of the dark matter signal that we thought about. And so we have to revise our methods and strategy to discover dark matter. So if you think that this is an artifact, we can move to the next slide. If you think that this is just an artificial example, you are wrong, because this pattern has been reproduced at least 3-4 times in the past decade. For the case of positron excess, you see a plot of the positron fraction rising up with energy in the top left. Well, now we know that pulsar wind nebula are a significant emitter of possibly explaining the totality of the signal due to pairs of electron-positrons accelerated in these objects. For the galactic center excess in gamma rays, maybe this is due to a yet unresolved population of millisecond pulsars. These are neutron stars that are rotating very, very fast around their axis. And for the antiproton excess, there are many possible culprits from a too rough description of the background to a too simplistic treatment of the correlations in the experimental errors. So I won't go through each one of these examples. I could spend at least one lecture for each one of these examples. I'd like to give you a more positive and view of what's going on in the community right now and what are some perspectives for the near future. So next slide, please. So that's the road ahead I want to spend some time on, especially for the students, because maybe some of them are interested in this type of research, and you might know what's my take on the trends that are currently being investigated. So next slide, please. I would say that there are two types of trends in the community that are being pursued. The first one is sort of pursuing the same ideas, but fine-tuning them or exploring them in specific, more narrow corners of parameter space. So in this point of view, the WIMP or WIMPy ideas are roughly correct. There is something, the gist of it is actually right. However, we have been sort of unlucky. So maybe there is some sort of fine-tuning or mild fine-tuning, or maybe, you know, the particles that are responsible for dark matter are just beyond reach and have not been directly produced at colliders like LHC, and have not been observed directly at, say, Fermi, because they are too heavy. And so they mostly produce photons which are too energetic to be in the bulk of the photons seen by Fermi. If this is the case, the best hope here is from forthcoming experiments. Of course, in the long term, some successor of LHC for collider experiments, but in astroparticle physics, that would be, one example would be the Cherenkov telescope array, which is a ground-based imaging gamma ray telescope, which offers an order of magnitude improvement in the multi-TeV range for dark matter. Okay, so next, there is an alternative strategy that is also pursued by people, and that's to look for something completely different, sort of taking the point of view that this WIMP miracle is a red herring. It's just a coincidence, it's numerology, so we shouldn't give too much weight on it. And maybe the inspiration for dark matter models comes either from different sectors of theory. One example would be the origin of neutrino masses, or some other arguments of phenomenological interest. For instance, some discrepancy between the cold dark matter model and observations at very small scale, let's say subgalactic scale. Some people think that this might be telling us something on the nature of dark matter. Some other people claim that's probably related to our limited understanding of the baryonic physics and astrophysics, but let's keep an eye on it, okay? So let me go in the next slide and the following part, let me go through example of these two type of strategies. But before doing that, let me add one comment. The comment is that even if you, actually, the standard simple WIMP dark matter candidates that I've been talking about, they are not ruled out in any way by indirect dark matter search results, okay? So why the community is sort of partially moving away from them, that's not by itself because of the negative results of indirect dark matter searches. It's rather because none of the other probes, say collider physics in particular, has given any evidence that there is new physics at the TeV scale, and nor direct detection, by the way. So the fact that we have seen no evidence, although we know that there is new physics, there must be new physics, we have no evidence that this new physics is at the TeV scale, so people start to be less and less warm about the idea that maybe the dark matter problem is solved also at the TeV scale. That said, so it's perfectly fine to devise a research program in WIMP searches, say at the multi-TeV range in particular, and there is ample space in plenty of space in parameter space to justify it. However, what's going on, I told you that there are these backgrounds, these nasty backgrounds, and we are more and more limited by the systematic error with which we know these astrophysical signals. So we are trying to squeeze the best we can out of it, but if we go to the next slide, it's fair to say that the return over investment is shrinking. So you need to work more and more in terms of modeling, on astrophysical understanding, and in the time scale for your research project, in terms to gain less and less in parameter space. So be aware of this limitation. So once I told you about this caveat, we can move to the next slide, and I want to show you one example where we can take advantage of the existing or planned instruments to gain some sensitivity to WIMP dark matter. So a notable example is given by the dwarf spheroidals. Okay, these are satellites of the Milky Way, some of which are illustrated in the diagram at the right, and they are characterized by a very high dark matter to baryon ratio. That means that there are much less contaminants by stellar phenomena than in the Milky Way. And this is good because we expect that the backgrounds come from stars or I don't know, binary objects, supernova remnants and the like. And since these objects are poor in these type of objects, we can expect that the dwarf spheroidals are poor in terms of background. So the signal to noise should be maximal for these objects if you are looking for dark matter. And in fact, this is confirmed by the fact that the current gamma ray limits are dominated by these type of probes. In particular, if you look for an excess in gamma rays, not from a single object, but you stack them together. So next, please. This diagram that you see here is a current bound of the annihilation cross-section versus the mass for the Fermi LAT collaboration. That's the black solid line. And what the diagram is showing you in dashed curves of blue shades are forecast for the improvement in these bounds if you were to use many more dwarf galaxies. Okay, you go from 15 up to 60 galaxies. And this is actually something that is going to happen most likely because of future surveys like the LSST, now the Vera Rubin telescope. It's expected to discover maybe a few hundreds of these satellites, and maybe 60 or 50 of them will be useful for dark matter research. And so just because of this inertial improvement in other sector of astrophysics, you can expect that the bounds will improve maybe by a factor 3. And not to speak of dedicated searches with new instruments such as the CTA that I already mentioned. However, that's the caveat I was mentioning. This will be eventually background limited, okay? And background limited means that there is anyway some background coming from the intervening signal from us to the dwarf galaxy because the line of sight crosses the galaxy, our own galaxy, right? So it doesn't mean that these observations are zero background type of observation. So since in order to model the background, we have to resort to astrophysical models, this will introduce a sort of intrinsic limitation to what you can do. So one alternative way that we have been exploring even here at my lab in recent years is to rely only on data-driven techniques in order to assess the background with non-dwarf galaxy direction and build empirical models, if you wish, of the backgrounds without relying on astrophysical modeling. And more recently, we have extended also this technology to the reconstruction, the dark matter distribution in the dwarf galaxies. So this is just one example of the type of technical improvements that you can expect to happen in the coming years, trying to get the most out of these additional observations or additional discoveries of dwarf galaxies in this example. Next slide, please. There is, of course, the alternative that WIMPs are not the answer to this problem. Of course, we cannot relax the assumption, the hypothesis on the dark matter, any of them, right? We cannot say that the dark matter is not stable anymore for the simple reason that otherwise it would not match the observed stability of this structure over the lifetime of the universe. However, we could easily relax the hypothesis that these particles were interacting strongly enough to be in equilibrium with the standard model in the early universe. Okay, so if you just tune the interaction strength to lower and lower values, at some point, the interaction strength would not be fast enough to keep these particles in equilibrium with the standard model. Alone, this simple tweak of the model would be enough to explain not only the fact that you don't see a signal, say, in Fermi or in IMS, but also qualitatively is consistent with the fact that we have seen no new physics at LHC. And you might look at this paper here for a more extended discussion at this point, but basically the idea is that the same type of cross-section that is controlling the rate of interaction in the early universe is also sort of proportional to the rate of events of new physics that you might see at LHC. That said, the problem becomes where to search, how to search. So that's the next slide. We have a huge parameter space, as I said, from 10 to the minus 20 electron volt or so, up to tens of solar masses. This is a line of mass space in dark matter models by Graciela Gelmini. And you see in red many, many candidates of dark matter spanning orders of magnitude in this diagram. And of course, it's impossible to envisage a single strategy to look for all of them, right? So you must be a little bit now more specific and try to, for instance, for very light dark matter particles, you might hope to see some quantum effects at astrophysical scales. For very heavy dark matter candidates like primordial black holes, you might hope to see some effects of the granularity of the dark matter, which is not a particle anymore, but it's a macroscopic object. Right, so the qualitative picture that is common to all these non-WIMP candidates is that it's harder in general to search for them with colliders, and often also with direct detection, although there might be specific direct detection techniques suitable for them. That's the case of axions. And as far as collider searches are concerned, usually the precision measurements win over the energy frontier and the mass, the kinematic mass space that you can open up. More frequently, these candidates show peculiar indirect signatures. For instance, a sterile neutrino of, say, tens of keV it would be unstable with a lifetime much longer than the life of the universe, but would emit would have a decay channel in neutrinos, active neutrinos plus photon, and this photon would fall in X-rays. Okay, so you might search for X-ray lines, searching for sterile neutrino decay, or you might have a peculiar astrological and cosmological signature. This is the case for warmer dark matter or primordial black holes. So if we move to the next slide, I'm getting close to my conclusion. The good strategy whenever you have a very broad parameter space and you don't know exactly where to search is to go for something unexplored, and usually you will learn something new. A good example is given by the opening of the gravitational wave window in relation with the possibility that dark matter might be due to primordial black holes. Actually, this possibility is almost ruled out. There is some residual part of parameter space where it's viable, but most of it is ruled out. However, the opening of gravitational wave windows has pushed many groups and people to revise some of the arguments that were used to study this possibility. And actually, some of them have been proven to be flawed and incorrect. So we have actually learned something because, I mean, pushed by the discoveries of a new astrophysical window. And this is probably going to repeat whenever we will open the realm of 20 centimeter cosmology in particular, or maybe improve over the old Kobe upper limits for the cosmic microwave background spectral distortion. You also heard about that yesterday, but there is a huge parameter space to be investigated, and there are some dark matter models, in particular light ones, which might show up in this channel. Okay, so let me come to my conclusion. That's my next slide. I tried to review a little bit what we know about dark matter, and also the traditional arguments relying the dark matter to the beyond standard model physics at the electroweak scale, dubbed WIMPs in general. I argue that we have not discovered them, neither at direct detection, nor colliders, or indirect detection. However, in particular for the indirect detection channel, we have reached meaningful exploration power. So we are now digging into interesting parameter space. At the same time, improving over this current status will require lots of efforts. Okay, it will partially come for free in the sense that there are already ongoing missions and efforts that will increase our data. But to beat the background limitation will require some hard work from the theory side and also from the data analysis point of view. So there is more and more machine learning, for instance, procedure used in this context. I also argue that there are alternatives to dark matter WIMP candidates, and these are being considered more and more. I think sociologically more as a result of the negative searches for new physics at colliders than by negative searches of dark matter at indirect detection. And typically, the motivations for these alternatives are to be found either in different type of physics, say the origin of neutrino mass or the axions and the strong CP problem, or by reference to some open phenomenological questions or some anomalies, say the small scale discrepancy at the core of the galaxies or the number and statistics of satellites. And they have stimulated new type of modeling, so some sort of self-interacting dark matter, some dark forces with light mediators in the dark sector, and so on and so forth. And especially if you want to focus on this second class of candidates, there is all the interest in the world to open new windows and explore further some existing ones which have been a bit neglected in the recent years. So examples of these, I didn't discuss them all, but the MEV gamma ray sky, basically we have 30 years old data about that, and the current sensitivity is orders of magnitude worse than what provided by, say, Fermi in the GeV sky. Gravitational waves is a new window, okay? The 21 centimeter cosmology, I just flashed this, but this is another important frontier. So we are talking about very long wavelengths in radio astronomy. The CMB spectral distortions, I mentioned also X-rays, actually a new, very performing detector in terms of energy resolution and field of view would be great for some dark matter searches as well. And also another window which I didn't mention is the, say, hundreds TeV to PeV gamma ray exploration, which is something that might reveal some heavy candidates, non-thermal candidates. And this can only be pursued from the ground. There are experiments such as Oak in Mexico or the forthcoming LASO in China that are particularly good for this type of window. So I will stop here and take some questions, please.
Thank you, Professor. Actually, for throwing light in a piece of puzzle, which is keeping physicists engaged for quite a long time, and we don't see any, that way ray of hope at the end of the road, because we are really confused which way to go. And as you said that the parameter space is really shrinking, and we have to look for other ways how to get to the real solution. So I would like to take the questions. May I? Yeah. Okay. So somebody is asking, can exions in strong magnetic field turn into gamma rays?
The answer is yes. Well, gamma rays, not necessarily gamma rays for sure, but also X-rays, for instance. So this is a possible strategy of search. And actually, the converse is true as well. So gamma rays may disappear into axions. Some of the search strategies, in general for axions, not necessarily for axion dark matter, rely on this process. This is one of the possibilities. So, for instance, if you have a very powerful gamma ray source, it may be that above some energy you see a peculiar spectral shape, some sort of analogous to a bathtub that you might have seen in the neutrino lecture. This might be a signature of a conversion into an axion. Or you might have an opposite type of phenomenon. For instance, we know that the sky is opaque to the extragalactic sky is opaque to photons which are more energetic than, say, a few TeV. Okay, so imagine that you now have I'm just making this up, right? But imagine that you have an AGN that is shown to have so this is a galactic nucleus. So basically it's a phenomenon associated to accretion of a supermassive black hole. And this has some typically pattern of activity in, say, radio, optical. So the flux is not constant. It varies with time, right? So imagine that now, and we know that these objects are extragalactic. Some of these are maybe hundreds of megaparsec away. So we know that at these energies, the sky is opaque, right? So to gamma rays. Imagine now that you have an instrument and it detects photons of, say, 100 TeV coming from this object. Okay, what would be a possible explanation? A possible explanation is that near the source, you not only produce photons, but you also produce some axions because of the mechanism we just mentioned. And what happens is that the photons will get absorbed on their path to us. However, the axions, they propagate freely, right? Once inside our galaxy, there is some magnetic field in our galaxy, and through this back conversion, some of these axions may convert back into, say, 10 TeV photons. And now we may immediately be seeing some impossible gamma ray source. So this is just one example of things that might happen rather unexpected and might shed some light on new physics in general. So in this case, it would be very hard to prove that this axion is also the dark matter. But at least let's start with discovering some new physics, and then we will we will discuss these additional problems. Okay.
Yeah, Professor, may I request you to put on your video? I mean, we
yes.
are.
I don't know if you see me. I mean, my video is on as far as I'm concerned, but I don't see myself. I don't know what's wrong.
Okay.
You see nothing, right?
We don't see anything. We see a P.
It's strange because as far as I'm concerned, my video is on. So let me see if I can
put it off again.
Yes. So now it's off.
Okay.
Now it's on, but for some reason you don't see me.
So I would like to take the second question.
Okay.
Somebody is asking, is the dark matter particles bosonic or fermionic?
Good question. Actually, we don't know. As far just because I told you, basically the all manifestation that we have of dark matter is at the classical level, the macroscopic level. You know that in order to differentiate between dark matter, bosonic or fermionic nature, you need some quantum phenomena to kick in. And as far as we know, both hypotheses are compatible with the dark matter. However, it's fair to say that the bounds are different if the dark matter is fermionic or bosonic. So if it's fermionic, for instance, we know that there is a lower bound to the mass of the dark matter, which is of the order of keV, a fraction of keV, okay? And that's basically coming from the fact that you cannot store an arbitrary number of fermion in a given phase space, as you know. If it's bosonic, it could be very, very, very light. In fact, it could be even 10 to the minus 20 electron volt or so. And that, if that's the case, you would be able to see manifestations of the quantum nature of dark matter on astrophysical scale. So there are some people that, for instance, think that the fact that dark matter distribution seems to be a little bit more chord at the center of galaxies than what simulations predict. Maybe this has to do with the fact that the cores are sort of solitonic effects due to the fact that the dark matter has a de Broglie wavelength of the order of a kiloparsec. So these are called fuzzy dark matter models because of this fuzziness. And that's an actively investigated class of candidates. But again, we have no strong evidence in favor of each model. Anyway, we know that if dark matter is very light, if it turns out that dark matter is very light, then it can only be, so lighter than, say, 100 electron volt or so, it must be a boson. But until we discover it, we don't know.
So, in fact, these all are open questions, and still, really, in proportions, we don't have an idea where we are standing in the search of dark matter. But Professor Pasquale has already shared a lot of information with us. So, any more? If no more question, I don't.
Yes, can I ask?
Yes, sure. Devojyoti, you can ask. Sure.
Actually, I want to ask in the previous day's lecture, Professor Gopakumar talking about the quantum gravity, and there actually there is something quantizing gravity. There is a work by Stephen Hawking about the Hawking radiation. So is there any relation about, is there any dark matter relations from the Hawking radiation? Can we get the dark matter particles if we detect sufficient Hawking radiation? And there is another question actually, that is we are experimentally find the Hawking radiation using the acoustic black holes and Bose-Einstein condensate. So is there any analog of that kind of dark matter particles we can find in our analogous cases?
So that's a very broad question. Actually, the answer is yes, in the sense that if the dark matter is, for instance, in the form of primordial black holes, actually that might be the only way we can see Hawking radiation from black holes whatsoever, because for the simple reason that astrophysical black holes are just too massive for this radiation to be of any relevance. While if dark matter would, if dark matter is in the form of primordial black holes which are light enough, by light I mean something like an asteroid or a comet size, then you might have a chance to see its Hawking radiation, so the evaporation through Hawking radiation. And actually there are several searches for this in X-rays and in gamma rays. And some of the best bounds on masses, say around 10 to the 16 to 10 to 17 grams, come in fact from the fact that we do not observe the Hawking radiation associated to these candidates. And as a result, there should be an upper limit to the amount of dark matter in the form of this primordial black hole. Let me say that in general, it could also be that dark matter is made of several components, right? Just like the visible sector is not just made of a one species, but you have protons and actually different type of nuclei and electrons and neutrinos. All these particles are stable. So it's perfectly conceivable that, from the early universe, you have several types of relics. Some might be primordial black holes, some might be sterile neutrinos, some might be WIMPs. Of course, this is often not considered for simplicity, because we still believe that, randomly I mean, if you think of it in a random sense without any strong prior, you still expect that one of these components will dominate the totality of dark matter. But it's perfectly possible, that say axions exist, but they are not responsible for anything appreciable of dark matter, or primordial black holes exist, but they are 10 to the minus 10 of the dark matter, etc., etc., etc. So I would separate the two questions in the sense that it's possible that we will see Hawking radiation from primordial black holes, and that they might contribute to dark matter. How much? That's a different story. And as you probably know, primordial black hole scenarios are exponentially sensitive to the details of the theory. So it's extremely hard to get just the right amount of primordial black hole. Of course, we don't know. I mean, nature must have chosen some parameters, so we don't know if it's the correct one. But it's much, much easier to say underproduce primordial black holes than to just get the right amount of dark matter. So this is still open, I mean, current subject of research. For the acoustic analog, I'm afraid that I mean, never thought about that. But even if there is anything like that, I mean, there is no propagation of acoustic waves in the astrophysical settings, basically. So we will never know if anything like that takes place in some region of space. So the best next shot is through gravitational effects. Okay.
Yep. Actually, previously, Professor Gopakumar actually said about the quantizing gravity as the field quantization of anti-de Sitter space, actually, and that level actually, can we see the a quantum effect of the dark matter particles, actually?
Well, we can see quantum effect. I mean, I mentioned one quantum effect that might be related to the non-localization, say, of it's basically Heisenberg principle. There is another possibility that dark matter is produced through quantum effects. So I mentioned there are at least conceivable models where dark matter only interacts gravitationally, right? So in that case, how do you produce it? And actually, this is a nice exercise in quantum field theory in curved spacetime. So if you have just a massive particle, very massive actually, and you have a period of rapid expansion of the universe, so we are talking about Hubble parameters much larger than what we have now, well, you might produce particles just by the analog of the Schwinger effect. So you can think of it as the fact that in a certain sense, you can convert the gravitational energy into the production of particles, okay? And it might be that you get the right amount of dark matter just through this process. You have just a Lagrangian of dark matter minimally coupled, so a massive particle minimally coupled with gravity, but a particle which maybe it's 10 to the 15 or 17 GeV. Well, if the universe was, inflation was taking place at this scale, and you experience some Hubble rate which are just right, you can produce dark matter through this gravitational production, analogous to it has some similarity to the quantum phenomena like the Hawking radiation or the Schwinger effect in electric fields. And some people use this mechanism, maybe, I mean, you're probably too young, but early 2002 or so, there were some claims in a Japanese experiment, AGASA. This is an extensive air shower experiment detecting cosmic rays at very high energies. They were seeing cosmic rays of energies superior to the one that would cause photopion production of protons on the CMB. So the current understanding is that the cosmos is opaque to cosmic rays of energy above, say, 10 to 20 electron volt or so. So if they were measuring events of higher energy, they should be probably local and of exotic origin. And one of the possibility was this very heavy dark matter particles. Sometimes they are called the Wimpzillas, so the Godzillas compared to the WIMPs. That was one of the explanations that was put forward. Unfortunately, this has not been confirmed because of some calibration issues, but it's still possible that instruments like, say, Pierre Roger would see some tiny fraction of neutrino or photon type of events, and this might be associated to a decay of very, very heavy particles. Okay.
Okay. Thank you, sir. Thank you very much.
Next, I wanted to ask something.
Sir,
Yes.
Yeah.
sir, I have a doubt. Are we living in a simulation? Because whenever we encounter something, we try to seek is the information it carries or the information it can carry.
Well, I mean, I don't think this has particularly to do with the dark matter problem. It can be applied the same remark to any aspects of natural life. I mean, as far as I can only tell you that if it's a simulation, it's a much better simulation than any one that humans have devised, because I mean, we cannot even figure out the rules of the games from inside. Well, yes, I still don't see how this helps answering any question. So it's a bit like the anthropic principle, right? Is there any prediction that one can make out of the hypothesis that we are living in a simulation? If not, it's just a philosophical point of view. It's not a question in natural science. But I'm ignorant, so I'm really asking if there are experts that can tell you a way to probe the fact that we would be living in a simulation. That's not really related to dark matter, but it's an interesting question, and I can only tell you that for dark matter is actually the proof that probably no human has designed this simulation. Otherwise, she or he would come out with the answer and get one or more Nobel Prizes. And so, since this has not happened, probably it's beyond us.
Yes, sir, I got it.
Okay, so like we have come almost to the end point of the program, and I would like to thank Professor Pasquale for his nice deliberation on a major issue.
Sorry for the technical problems. I don't know.
Yeah,
It was very hard.
Because you also got disturbed. Your schedule also got disturbed, and I had to disturb Professor Goswami. So right now I can see 4 of the experts here in this forum. So I would like to request Professor Rajodri to say a few words to conclude. I would like to hear actually from all experts about the event and how we can the discussion forward. Professor Rajodri.
Well, you should hear from the others, but I think it's been a very nice experience. I have not heard all the talks, but I did hear some of Subhabhati's talk today and also Pascal's. I missed Nambada's talk, though I think I've heard it before. What is important is that I think all of us, we have tried to convey to the students some of the excitement, some of the puzzles in modern particle physics and gravity and so on. So I hope students, you enjoyed it. There are a lot of questions from which I can see that we have at least been able to set you thinking. Please do continue thinking. Please think more. And some of you may want to take this up as your lifetime career. I'm sure, the more you learn, the more you hear about these things, the more excited you are. And this excitement and this curiosity is what drives science. It's what has driven us all to careers in science. It is what has driven the great scientists who have made major contributions to do science. And I hope that's the inspiration we have been able to give you. I really want to thank you, Athri, and your department and your dean for creating this opportunity for the students, for us to tell you about what the things which excite us, and also for everyone who attended this. To have, I think, what I hope was a very fruitful session. So thank you, everyone.
Thank you, sir, for all the interests you took and all the guidance that you have given to shape this program.
Oh, you're almost right. I did very little. You people know the hard work.
That also matters.
And the speakers have all very kindly agreed, without any.
I would like to hear from Professor Mondal. He is the senior most, I think, in the speaker list. Sir, you are there?
I'm here, and I think thanks for your you and your department for organizing this webinar, and it's wonderful. I think this is one of the positive points of this COVID situation, that there are many talks are going on, and then students have the opportunities to hear these talks. And I found basically these students are very attentive and they're inquisitive, and the question they're asking is actually sometimes asking actually forcing me to think before answering. So it was really wonderful. And as Sridhar has said, I think you should continue this. It is you that who has to carry the flag of science and continue the good work. And so continue, attending such meetings and asking such questions. And hopefully sooner or later you will be yourself directly involved in research, and so you will be giving the talks again. And thanks the department for organizing this very good meeting. I have not attended all the talks. Yesterday I have attended 1.5 talks, Sridhar, and half of Gopakumar talks, and today I attended all the 3. So it's a nice really experience for me. Thank you.
Yeah, we try to keep it in the basic level, so that advanced talks are available. Most of the times they are beyond the reach of general students. So the main aim was to create an interest in the average level students, so that they can also think of doing something else. So that was the main aim, and I hope we could go at least a little step in that direction. I would like to request Professor Goswami to share her experience.
Thank you, Atri. I think it was a very good program. You have planned it well, and also Sri Rubda might have advised you. And because you had a lot of topics of current interest, and cosmology, neutrino physics, standard model, experimental, so it was a good balance. And I thought that I did not plan to attend all the talks, but the talks were so good, then finally I ended up attending all the talks. And I think this timing was very helpful for me, because if it was during the institute time, then it would have been little bit clashed. So that way I think this was a very good timing wise. And also I reiterate what others said. I was very impressed by the questions and the attention that the students gave to the talks, and they asked really good questions. And as Naboda said, sometimes it made us think also that what could be the answer to the questions. So in that sense, I really enjoyed the program, and I am happy that I could attend all the talks, and it was a very good experience for me also. Thanks.
Thank you so much. Professor Pascal, you talked for an hour. Now I am requesting even you to share the experience. I would like to thank you. Actually, basically, you agreed to speak, and in a topic which is of really in the forefront area, and all are basically the forefront area. We have designed it this way, but you could spare time and come here and speak to the students. What is your suggestion towards the department, so that we can
No, I'd like, first of all, to thank you again for contacting me and offering me this opportunity. It was great. And actually, one thing that everywhere in the world is, it's a common problem. I think that students and young scientists are suffering the most of this situation. But your effort goes in the direction to actually offer even new opportunities that might be hard to come with in normal times. So I appreciated not only the organization of the meeting. I followed some of the talks as well, but in particular the participation of the students and the questions. And personally, I think that's our best hope for solving some of these riddles, that some new bright mind can come up with original way of thinking about the data and the situation without being too biased by the the paths that were taken in the past, looking with some fresh eyes, and being at the origin of the breakthrough of tomorrow. And personally, I'm very optimistic that we will get exciting progresses in the field in general of astroparticle physics, which I see is blooming. But even particle physics that seems to be facing a sort of stop, I think it will bounce back with some new smart idea of how to accelerate and detect particles much more easily than we do now. So no matter what's the passion that you have in science, I think this is a wonderful time to work on it. And there are many things that we don't know. And I would just conclude with the hope that maybe I will meet soon some of you in person, because online type of events are great, but we need also personal contacts to foster some collaborations and faster progress. Thanks.
Absolutely right. Yeah, physical meeting is the best possibility, but given the current situation, it's very difficult to think of something like this in near future, and that is why we are just trying to do something over the web platform.
We are used to think about the unthinkable, right? That's our job.
Yeah, that is true. I would like to hear from some of the participants how you like the event. I know it's late and I'm holding people back over time. And then may I request any one of you to share your experience or whatever, how you like the event, or you have some suggestion you want us to organize some more, or like anything. Any of the participants, please.
Hello.
Yes, Devajyoti, please.
Yeah, actually, this is a very good seminar, good webinar to boost my views about this field. Actually, I am actually just completed my graduation, and so and I just in our last semester actually just heard about the field of particle physics, and now these type of webinars, these frontiers of particle physics, actually very much boost my views and my interest about this type of fields, about field of gravitational physics, about general relativity and particle physics actually, and that give me a very very good enthusiasm about the subject actually, and a lot of hope about my future career about this subject and about physics actually. And I think in future we will hear a lot of this type kind of seminars, this kind of frontiers from more and more.
Thank you, Devajyoti, for sharing your views. Yeah, I mean, as a part of a department's Silver Jubilee, it is university as a whole. Different departments have come up at different points of time. So, department is celebrating the Silver Jubilee, and as a part of celebration, we are trying to organize different programs. And if you have a look, everything is finally uploaded in our YouTube channel, so you can keep an eye, or you can keep an eye in the department website to get information about the programs. Meanwhile, anyone else who would like to share their experience quickly?
Well, now that you have started, you should continue this. You should not wait for the Golden Jubilee to have the next program.
Yeah, sure. Yeah, Nidhi, you want to say something?
Yes, I want to say that this session was very good, and it will lead us to, as I'm a MSc student, and it will lead us to think more about the things about the standard model, which now we are thinking about that the things, new particles, how we can discover these things.
Okay, Nidhi.
Yeah.
Yeah,
Yes.
thank you very much. Any international participant in the arena? I mean, outside India? Anyone? Anyone in the platform outside India? Because I could see participants, at least 10 of them from Bangladesh and from Germany and from Canada. I could see the registrations. So anyone here?
Hello, Professor.
Yes.
I'm Shumit from Bangladesh.
Yeah.
This kind of workshop actually, I mean, it's so much important. You can even think. I just want to share a story. Just last year, I had the chance to attend lectures of Professor Rai Chaudhuri. Last December, he came to Bangladesh in winter school. And from there, from his lectures of standard model and electroweak interaction, I literally got inspired. And now I am doing thesis on I am doing standard model. And in your previous seminar on group theory, I attended, and that's just my life goal now. So I think this kind of seminars or opportunity of hearing you professors is more than you can even imagine. And I just waited for 7 or 8 days to just attend and hear about neutrinos and the standard model and dark matter. And I really appreciate and very much thankful to you all. I think and I believe and I hope that I can contribute something in the future. So thank you a lot. Thanks a lot.
That's very good. I'm very happy to know this. Thank you.
Yes, Professor, even I wanted to share this with you, but now I think I have the platform, and it's just my case. You can't even imagine that many of my friends even are following your lectures, and your stories about spontaneous symmetry breaking just inspired me so much that even I talked to my professor instantly.
Very happy to know that. Of course, you also had beautiful lectures by Ashok Sen and others in that.
Obviously.
So I hope you enjoyed that, and I hope you enjoyed the things today, because it was a different kind of thing. That was more teaching. This is more to give you an overview. But it's good that you know, and I'm very happy to hear that you are inspired by this. Please continue, and I'm sure one day perhaps we will be listening to talk from you.
I also hope so. Please pray for me, and I will try hard. I assure you that.
Sure. All the best.
I think people are writing thank you messages in the chat box. I seriously, sincerely believe that it was beneficial for all of the participants, and for me, I am really happy that I could organize this. I could make people meet in a platform, and I would like to thank the speakers especially that they have agreed so readily to the invitation, and we could really have this here. And this, as I already told, that this basic type of talks overview is sometimes very important for the students to get a picture of what is going on around us. And I would like to thank once again all whoever is involved on behalf of the department to make this event a very successful one. May we stop here for this time, and I hope that we will come back with a different program very soon. Yeah, so again, I thank Professor Rajaudhuri, Professor Mandal, Professor Goswami, Professor Serpico, and Dr. Khatri and Professor Gopakumar could not make it to this concluding session. Anyway, we also got delayed due to some technical glitches, but this has also a part of the story. We can't help much. So thank you once again, and I declare this webinar over. Thank you.
Thank you. Bye, O3. Bye, everyone.